Alrighty, howdy folks. This is section 5.1, chapter 5, section 1, area under the curve. How should I put it? There's going to be a bit of a theory in this one. Okay, for quite some time I will be only addressing theoretical aspects, and finally I will solve a couple of problems. So, to give you a heads up, you kind of have to understand the theory part of it. And what I certainly want from you is to be able to solve the kind of problems that I do at the end. So there is something called finding the Raymann sum and taking the limit of it as n approaches infinity. That's what I want you to be able to do. All right. So without much further ado, let's start with this one. Area under the curve. One of the first things that you need to understand is how do you split an interval? Right now, I'm showing you an interval 1 through 4, right? 1 to 4, a closed interval. And I want to split this into 3 equal intervals. Do you see how I have 3 equal intervals? Okay. Now, if I have 3 equal intervals, in this case 1 to 4, what do you think is the width of each sub-interval? Can you figure that out? The width of each sub-interval is 1, right? How did we get 1? 1 is true because if the width of the interval is 1, then the second point, this point, would be 1 plus the width, which is 1. 1 plus 1 is 2. 2 plus 1 is this 3. 3 plus 1 is 4. Yep, so that works out. So now the question is, how did we figure that out? Is there some kind of a formula that we can come up with? How many sub-intervals did we split this into? 3. Okay, what's the width of this whole interval? Does the question make sense? What's the width of this whole interval from 1 to 4? Oh, 4 minus 1. Right? 4 minus 1 is 3. And we split this into 3 subintervals. So 3 divided by 3 is 1. So that width of that subinterval is called delta x, the change in x. Okay. And that when we split this into 3 intervals, delta x turns out to be 1 because that is the width of the whole interval 4 minus 1 divided by n. Cool? And also, when we do that, would you agree that we end up with 4 points? Like this 1 is one of those points, this 2, 3, 4. Each one of those things is a point that we end up getting. So let's call them x sub 0, the left endpoint. The next one is x sub 1, is x sub 2, and x sub 3. Are you cool with that? So this is one of the first things that you need to really understand. How to take an interval and split it into sub-intervals. Cool. What's the value of x sub 0? Whatever is the left endpoint value, which is 1, so x sub 0 equals 1. Cool. How do you get x sub 1? Well, x sub 1 is nothing but this 1 plus delta x. Delta x happens to be 1, so 2. And x sub 2 is 3, x sub 3 is 4. Okay. Now, I'm going to split this into, how many intervals did I split this into? 1, 2, 3, 4, 5, 6. Oh, I split this into 6 sub-intervals. I should be careful and say sub-intervals, not intervals. But I hope you get the idea. Okay. Again, what's the whole width? The total width is 4 minus 1, 3. But we split this into 6 intervals. So what should the width of the subinterval be? the total width 3 divided by 6. So delta x should be 0.5. And the moment we get that, we have these points x sub 0, x sub 1, x sub 2, x sub 3, all the way up to x sub 6. And like we did previously, let's figure out what each one of those things is. Would you agree? X sub 0 is 1, x sub 1 is 1.5, and so on. And also x sub 4, 5, 6 would be like that. Right? Okay, now that we are armed with this information, can we generalize based on these specific cases as to some seemingly complicated looking thing, but the whole idea is still the same? So the idea is, suppose we were to have an interval from A to B, and we split this into n subintervals, equal subintervals. Then that would generate a whole bunch of points. In fact, it would generate, any idea how many points? A bit of a trick question, slightly tricky. How many points did we generate when we split this into 3 intervals? We generated 4 points. 3 intervals, 4 points. Cool. When we split this into, did we actually have 4 points? Yeah, notice x sub 0 is one of those points. Don't say, hey, we just have x3, man. Well, there is x sub 0, man. So 1, 2, 3, 4. In the case of 6 intervals, we actually have 7 points. 0, 1, 2, 3, 4, 5, 6, all of them would be 7 points. So, would you agree that when we split this into n subintervals, we must have n plus 1 points? That's the idea. And how do we figure out delta x? That's an important question. What is the width of this whole interval? Right? Earlier we said 4 minus 1. So what should it be in this case? B minus A. That's the total width. And we are splitting this into n intervals. So the width of the subinterval must be B minus A, the total width, divided by n. B minus A over n. As simple as that. Right? So that's what I'm stating here. Given an interval AB, we split it into n equal subintervals, whose width is delta x equals B minus A divided by n. And what does that do? It creates n plus 1 points, namely x sub 0, x sub 1, x sub 2, all the way up to x sub n. Given by, I'm about to tell you what x sub 0 and x sub 1 and all of these things have to be. Do you know what x sub 0 needs to be? Simple. Whatever A is, the left endpoint is x sub 0. So x sub 0 is clearly A. Would you agree? Cool. What is x sub 1? Would you agree? To the left, to the point to its left, which is x sub 0, you just need to add a delta x. So x sub 1 is x sub 0 plus delta x. Cool. Okay, what about x sub 2? Oh, by the way, x sub 0 is A, so I said A plus delta x. I'm sorry. Okay, now x sub 2 is x sub 1 plus delta x. Would you agree? X sub 2, this guy, is whatever its previous value. You add a delta x to it, you should get x sub 2. But x sub 1 is already A plus delta x in the previous step. So, would you agree this should become A plus delta x plus delta x? Yep. And what is that? Oh, A plus 2 delta x. That's interesting. Cool. Let's go one more. X sub 3 is x sub 2 plus delta x. But in the previous step, we got x sub 2 to be A plus 2 delta x. So let's do A plus 2 delta x plus delta x. And that is A plus 3 delta x. Now, here is where you need to see a pattern. X sub 0 is A, X sub 1 is A plus 1 delta X, X sub 2 is A plus 2 delta X, X sub 3 is A plus 3 delta X. So in general, X sub I, what is I? I some 0, 1, 2, 3, anything like that. Can you figure out a general formula for X sub I? Would you agree? It should be A plus I delta X. If you really saw that, then pat yourself on the back. It's a wonderful accomplishment. Good. So X sub I is A plus I delta X. Typically, what mathematicians do is immediately state, what in the world do you mean by I, man? They have to answer that. So I is 0, 1, 2, 3, or all the way up to n. It can take on any of those values. To be more precise, mathematicians would say I is an element of the set 0, 1, 2, 3 all the way to n. Engineers typically write like this, so don't sweat it too much. Is this really true? Okay, we can always verify. Let's say I takes on a value of 0. Go to this thing on the left hand side. Plug 0 for I. So X sub 0, okay, equals A plus 0 times delta X. 0 times delta X is 0. So A plus 0, that's A. So X sub 0 is A. Is that right? Yep, it is. X sub 0 is A. Now if you say I is 1, this left hand side is X sub 1 is A plus 1 delta X or A plus delta X. Yep, that checks out. So in fact, it checks out for all of them. Right? And how do you calculate delta X? We already said that. The total width is B minus A. Divide that by how many ever intervals you split this into, sub-intervals you split this into. Happens to be n. Cool? So first, you must understand how to split a given interval into equal subintervals and be able to tell what the coordinates of each of those points would be. Okay? All right, let's go to next. I need to introduce something called sigma notation. Some of you may have already seen it, and for the benefit of those who have not, let me cover this. Okay, if a sub m, a sub m plus 1, a sub m plus 2, all the way up to a sub n are real numbers, and m and n are integers such that m is less than or equal to n. What? Simple, I know. There's something called a sub m, and the next one is a sub m plus 1, and so on, all the way up to a sub n. Let's say you have real numbers just like that. For instance, you could have 3, 4, 5, 6, 7, so on. Or 1, 3, 5, no, let me be careful. Yeah, 1, 3, 5, 7, 9, 11, and so on. Okay, or real numbers, m and n, such that m must be less than or equal to n. Okay, then this is the way we write that. The way you read this is sigma, that is the Greek symbol uppercase sigma, I equals m to n. How do you read this? Sigma I equals m to n of a sub I. Cool? Sigma I equals m to n of a sub I, and that turns out to be, this is how you figure this out. You will first let I take on a value equal to m. So now with that, go inside. You have a sub, now I is m. So a sub m, that's the first term. Are you cool? When we say I equals m to n, let I first take on the value of m, And so a sub I will become a sub m. That is the first term of this series. Then, because of the sigma notation, you should say plus. Cool? A sub m plus. Now this is what we're going to do. We will increment I by 1. What does increment I by 1? We will increase the value of I by 1. Previously, I was m. Now let's make it m plus 1. That's what is called incrementing by 1. So when we increment I by 1, we have m plus 1. So with that value of I, we go here and say a sub, m plus 1. Well, that's the second term. Plus a sub, again, increment even by 1 more, a sub m plus 2, a sub m plus 3, a sub m plus 4. You keep on going until m plus whatever it is equals n. Until I becomes n. That's where you terminate this and you say stop. That's a sigma notation. Okay, I'll give you quite a few examples. Enough examples, I think. Examples. Suppose I were to say I equals 2 to 7 of a sub I. What would that be? Well, I should take on a value of 2 first, and we get a sub 2 plus a sub 3. We incremented 2, incremented I by 1, so got 3, a sub 3, a sub 4, all the way. And where do we stop? When I becomes 7, right? So that's one example. Let's pick up a slightly different one. What? You can apply sigma notation to something like this? Yeah, you can. So, what is the very first value of I? I should be 3. Take that and come inside and plug that value for I. So, would you agree? The very first term would be 3i, that is 3 times 3, plus 1. Yep, the first term is 3 times 3 plus 1. Now, increment I by 1, that is from 3, make it 4. So, with that value of I equals 4, come inside, 3 times 4 plus 1. Right? 3 times 5 plus 1. 3 times 6 plus 1. 3 times 7 plus 1. Nope. There won't be a 3 times 7 plus 1, man. The moment I became this upper limit 6, you stop. Right? So, the process terminates right there. And whatever this turns out to be, I'm not interested in figuring out that sum, but that's the idea of a sigma notation. Cool? I think I have one more example. Sigma I equals 1 to 4 of sine of I pi over 8. You tell me, what's the first term? What would be the value of I the very first time? Good. 1, right? So what's the inside stuff? Sine of 1 pi over 8, or sine of pi over 8. The second one, I becomes 2 now. Sine 2 pi over 8. When do we stop? When I becomes what? 4. Cool. We didn't reach 4 yet. So sine of 3 pi over 8, sine of 4 pi over 8. So now we have reached an I of 4. So we'll terminate the process. Sigma notation. Cool? All right. And then there are special sums. Sigma I equals 1 to n of 1 itself. What? Sigma I equals 1 to n of 1? Yeah. Huh. What do we do? Well, I takes on a value of 1 first. And with that I equals 1, we'll go inside and evaluate that stuff. Oh, that's just 1. Okay, when I equals 1, this stuff is 1. So that's why I wrote 1. Now let's increment I. When I equals 2, be very careful now. I gotta do an Elmer Fudd and go, be very, very careful. Right? The second, when I equals 2, guess what? This is still 1. That doesn't become 2. I became 2. But the inside stuff is just 1. So even for I equals 2, we have to say plus 1. I hope I didn't confuse you with that one. You must get that. Okay, when I equals 3, that is still 1 because this is independent of I. It is a constant. So we just say 1 plus 1 plus 1 plus so on. How many times? Well, I is going from 1 to n. So there would be n number of 1s being added in this case. And that's why I wrote n times. If I add 1 n times, how much should I get? Well, think about it this way. The moment somebody asks me a question like that, well, I don't know. Let me think. If I add 2 times 1 plus 1, what do I get? Oh, 2. Cool. If I add 3 times 1 plus 1 plus 1, oh, I get 3. Now based on that, I see a pattern. Oh, you mean 1 plus 1 plus 1, 1 plus n times would be n. Answer is yes. You're right. Cool. All right. Next. Sigma I equals 1 to n of I. So I takes on a value of 1. And with I equals 1, let's go inside. Oh, that is I. So that's 1. Now I becomes 2 because we always increment by 1. And so with a value of I equals 2, let's go inside and evaluate. Oh, that's I. So that's 2 plus 2. I becomes 3 and so on. So 1 plus 2 plus 3 plus all the way up to n. What does that equal to? I don't know. There are wonderful stories about this thing. Anyway, I don't have the time for a story. Sorry about that. And that turns out to be n times n plus 1 over 2. Okay. Okay. Don't have the time for a story. N times n plus 1 over 2. And then we could have sigma I square. In that case, we have 1 square plus 2 square plus 3 square all the way up to n square. Is there a formula for this? Yep, there is. And that turns out to be n times n plus 1 times 2n plus 1 over 6. Oh, by the way, let's go back to the previous one. Is that formula really correct? Or should you just simply take my word for it? No, you can always check. Let's say I pick 1 plus 2 plus 3 only. So that means my n is 3. Would you agree? If I say 1 plus 2 plus 3, I have my n to be 3. So 1 plus 2 plus 3 adds up to 6. Okay. Plug that value of 3 on the right-hand side into the formula. So you have 3 times 3 plus 1 is 4. So 3 times 4 is 12. 12 divided by 2 is 6. Hey, sure enough, 1 plus 2 plus 3 is 6. So this formula certainly worked for a case of n equals 3. If you want, check it for n equals 4 and so on. You'll find that this formula is in fact correct. So here, is this formula right? Again, let's pick 3 terms. 1 plus 4 plus 9. 1 plus 4 is 5. 5 plus 9 is 14. N is 3. 3 times 4 is 12. 12 divided by 6 is 2. Okay, so we have a 2 now. 2 times 3 is 6. 6 plus 1 is 7. 2 times 7 is 14. Yep, that worked out. So this formula is right as well. And sigma I cube is 1 cube plus 2 cube plus 3 cube all the way up to n cube. And folks, there's a formula for that as well. Quite interestingly, whatever was the formula for sigma I cube's formula is just the square of that. We have n, instead we have n square. We have n plus 1 here, we have n plus 1 the quantity square. We have 2 here, we have 2 square here. Right? Who would have thunk? That's a beautiful coincidence. All right. So this is some of the background that I wanted to establish before I actually get into Rayman Sum. Okay, there's something called Rayman Sum that we need to get to. And maybe I will pause here. All right, so we are back. And now let's continue with this concept called Rayman Sum. What in the world is this Rayman Sum concept? It's something like this. Suppose our desire is to find the area under this curve. We have this function f of x, the graph of y equals f of x. And on this interval a to b, in this case a happens to be 1 and b happens to be 5, but we could make it any general interval a to b. And by the way, that's why I needed to talk about intervals, subintervals, and all kinds of things. All right, so what is the area under this weird looking curve on this interval 1 to 5? So as you can see, that brown thing, that's the area that we need to figure out. Man, that's a weird shape. It's not like a triangle or a rectangle or a square or a circle. How can we find the area of something like that? Glad you asked. So, what if we were to just approximate this with one rectangle? What? Our area, our intention is to find the area under the entire curve. However, we'll say, well, what if I were to split this interval 1 to 5 into just one subinterval only and construct a rectangle? What kind of a rectangle? Well, the width of the rectangle is clear, 1 through 5, so 1 to 5, 4 units. But the height of this rectangle is going to be, pay attention to this please, the height of the rectangle is going to be whatever the function's value is at the left endpoint. This interval 1 to 5 has a left endpoint of 1 and a right endpoint of 5. So whatever f of 1 is, that's going to be the height of this. And if you are telling me, man, that's a pathetic approximation, you are absolutely right. We are supposed to have that much, and we are saying, well, that's kind of approximately equal to the area of this rectangle. Oh, that's bad. Okay, I agree. But what if we were to split this into 2 equal intervals, 2 subintervals? And we adopt the same process. We'll say, okay, now we have split this into 2, and again, we have 2 rectangles. The width of each rectangle is whatever is the width of that subinterval, 1 to 3, is one subinterval, 3 to 5 is the other subinterval. What's the height of each of those rectangles? Whatever is the function's value at the left endpoint. So for the 1 to 3, the left endpoint is still 1. So f of 1 is the height of the first rectangle. Whereas for the second interval, we have 3 to 5. The left endpoint is 3. So f of 3 is going to be the height of that rectangle. Okay, is this any better than the previous one? It seems so. It's not still good at all by any stretch of the imagination, but definitely better than splitting it into only one or leaving it as one interval. Right? Let's see what happens if we were to go to 3 intervals. Oh, here the concept is once again the same. The width of each of these rectangles is whatever is the width of that subinterval, right? The delta x that I talked about. The width is delta x, and the height is whatever is the value of the function at the left end point of that subinterval. Isn't this slightly better than the previous one? So, can we keep doing this? Keep increasing 4, 5, 6, 7, 8, 9, 10. Wow. Isn't it getting a lot better? It is. What if I were to go to 40? Still not exact, but it is much, much, much better. Would you agree? And in fact, I do have the exact values. The actual area is 19.2, but all these rectangles added up turns out to be 19.25. That ain't so bad. Would you agree? Okay. Now, so this is based on the left endpoints. This is the, by the way, the sum of these rectangular areas is called the Raymann sum. Bernard Raymann is a great mathematician, and so this is named after him, Rayman Sum. So Rayman Sum with the left endpoints is this. However, it's entirely possible to pick right endpoints. The concept is still the same. That means we have this whole interval 1 to 5. We'll split this into just one interval, which means don't split it. But for the height of the rectangle, use the right endpoint's function value. So f of 5 would be the height of this rectangle. Oh, this is pathetic, right? So compared to the actual area, this is definitely a bad idea. Okay, again, let's change this to 2 intervals, 3 intervals, 4, 5. Let's go all the way up to 50. That ain't so bad, right? It turns out the actual value with 40 rectangles is 19.13 as opposed to the exact value of 19.2. Cool? Or we could do what is called the midpoint. Now, what's the idea here? Our interval is 1 to 5, and the width of the rectangle is 1 to 5. However, the height would be whatever is the value of the function at the midpoint of this interval. 1 to 5, the midpoint is 3, so f of 3 is the height of the rectangle. Whoa, this is a lot better, it appears. And again, we can do a whole bunch of them, right? And then it turns out, at least to how many ever decimal places, just one decimal place, this is exactly 19.2 as the exact integral, did I say integral? The exact area under the curve. Okay, I said something like showed definite integral. I don't ignore the definite integral part of it right now. Area under the curve, actual exact area is 19.2. This midpoint apparently is giving 19.2. Maybe in the third or fourth decimal place it might be different. That's a different story. This is the concept I want you to get. To find the area under the curve, we can find the Raymann sum and say that is an approximate value of the area. Now, here is the coolest thing next to sliced bread. Having gone through this concept, we can now say using left endpoints, the Raymann sum R sub n is I'm claiming it to be delta x times f of x sub 0 plus f of x sub 1. Does that make sense to you? Well, for the first rectangle, would you agree that the left hand point was x sub 0? And so, what did we say the height of that rectangle would be? Whatever is the function's value at that left end point. So f of x sub 0 is nothing but the height of the first rectangle. And we need to multiply that by, that width by, the height by a width. Width is nothing but delta x. Similarly, the second rectangle's height would be the function's value at the left end point of that second rectangle, which happens to be x sub 1. And so on. So the nth rectangle would be f of x sub n minus 1. The n minus 1th point, excuse me, the value of the function at that n minus 1th point. Cool? So this is based on the left end points in a general case. And we can write this in sigma notation. That's why I had to introduce sigma notation. Delta x times, instead of writing this big long thing, we can use a concise sigma I equals 0 to n minus 1 of f of x sub I. Is that true? Let's check. Take I to be 0 to begin with. So we have f of x sub 0. That's precisely what this is. Then increment I by 1. So you get I equals 1. So f of x sub 1. So plus f of x sub 1. Because of the sigma, we have to say plus. Plus f of x sub 1. Plus f of x sub 2. Plus f of x sub 3. And so on. And we stop when we get to n minus 1. Cool. All right. So, Raymann sum with left endpoints. And what is delta x? As before, b minus a over n. How do you find x sub I that you need? X sub I is simply a plus I times delta x. We already discussed this, right? I would be 0, 1, 2, 3 all the way up to n. All right. Now, the right endpoints thing would be similar but not identical. The width times, for the first rectangle, it's the right endpoint's height, right? The function value, the first rectangle is at x sub 1, so f of x sub 1 we should say, and f of x2 and all of this. And so this gives us delta x times sigma I equals 1 to n f of x sub I, where delta x is b minus a over n. All of that is still the same. Cool. Yeah, this is fine. You can find the Raymann sum. But I thought we were discussing area under the curve. And here is welcome to Calculus 1. We have this wonderful concept called limits. What's up with that? how many intervals did we split this into? As I'm showing you? Oh, some n intervals. Okay. What if we were to divide this into infinite number of intervals? Now, did we notice that as we went from one rectangle to 2 to 3, 4, kept increasing, we got better and better values for the area under the curve, for the approximation of the area under the curve? So what if we increased even beyond that 4D? In fact, headed all the way up to infinity. Guess what? In that case, if you actually went all the way up to infinity, then you got the exact area under the curve. But what do you mean by dividing by infinity? Oh, limit concept helps us. You mean the width would be b minus a divided by infinity, man? You cannot divide by infinity. That's going to be 0 or something. Yeah, but that's why we use limit concept. So this is how you find the exact area under the curve. Cool? Now, I'm going to solve a couple of problems, and I want you to be able to solve problems just like this. Okay? I will be a very happy man if you learn how to solve such kind of problems. That's all I'm expecting you to do from this section. Are we clear, folks? Okay. So what does the problem say? Find the area under the curve f of x equals x squared plus x minus 1 over the interval 1, 3, closed interval, using the limit of the Raymann sum. Okay. We will do something. We will always use that right endpoint sum. What's that right endpoint something? This guy. Delta x times sigma I equals 1 to n of f of x sub I. Okay, that's what we will use. So, where delta x is this and all that. Cool. So, let's identify. What is A? Look at the problem statement and please tell me what is A. Oh, what's the interval? Interval is 1 to 3. So that means A must be 1 and B must be 3. Exactly. Okay, so we need A and B. We got it. And we are going to split this into n intervals, so we don't know what n is. Just leave it as a variable n. Can we find delta x? Yeah, delta x is b minus a over n. So 3 minus 1 over n. So that's equal to 2 over n. Simple. Identify what a is and b is. From that, go ahead and calculate delta x. Okay, next step. Can we figure out x sub I? There's a formula here. Do we know a? Yep, we do. I, just the variable I. Delta x? Yep, delta x is 2 over n. So clearly, we can find x sub I. Let me pause there for a second and ask you a question. Why should I find x sub I? Why should I find x sub I? Our objective is to find that Raymann sum. So do we need x sub I to find the Raymann sum? You bet. We definitely need x sub I because we need to actually figure out f of x sub I. That is what is expected of us. We need to find f of x sub I. Okay, to find f of x sub I, we need x sub I. So without much further delay, let's go ahead and do x sub I. That's nothing but a plus I delta x. A is 1, I is I, and delta x happens to be 2 over n in this case. So, ladies and gentlemen, x sub I is 1 plus 2i over n. Aha! Now let me ask you, can you figure out f of x sub I? I don't know, man. Well, check this out. Do we know f of x? Yeah, x squared plus x minus 1. So would you, if I were to ask you, hey, can you tell me what f of 2 is? Would you have any difficulty? No, you would say, piece of cake, man, f of 2. Plug 2 for x. And you say 2 squared plus 2 minus 1, whatever that turns out to be. If I say, what is f of negative 7? Plug negative 7 for x. So if I ask you f of x sub I, and x sub I happens to be 1 plus 2i over n, would you know how to find f of x sub I? Of course, you plug 1 plus 2i over n for x. As simple as that. That's exactly what we're going to do next. F of x sub I, wherever I see an x, I plug in 1 plus 2i over n. So 1 plus 2i is quantity square plus 1 plus 2i over n minus 1. Let me pause there. Let's take a good look at it and see if that makes sense or not. Right? Cool. So f of x sub I. Now let's just FOIL this out and simplify if we need to. 1 and negative 1 add up to 0. There's a 4i over n plus 2i over n. So that makes it 6i over n. And as this 1 will still remain. So that turns out to be 4i square over n square plus 6i over n plus 1. Are we any close to finding r sub n? Are we on the right track? You bet. Do we know r sub n? Apparently, from this formula, r sub n is just simply delta x times this sigma I equals 1 to n of f of x sub I. We already found delta x. We just found f of x sub I to be this 4i square over n square stuff. So let's just plug that in there and evaluate that sigma. We would be done. Okay, so let's do that. So delta x is 2 over n and sigma I equals 1 to n of this f of x sub I. If we can figure that out, we are done. If we can find this sum, we are done. Okay. Just to remind you of what it looked like, I reproduced it here. Okay. Can we find the sum? Check this out. It turns out if you have sigma of something plus something, you can find the sigma of each of them separately and add them. Okay, sigma f of I plus g of I is equal to sigma f of I plus sigma g of I. So we can do that. So that's what I did. First I split this into 3 different sums. Okay, fine. What's the next step? Well, the next step, pay attention to this part. Let's focus on this first sum. Sigma 4i square over n square. Is 4 a constant? Yup. Is n a constant? Well, I is the one that is changing. I is the one that's taking on values of 1, 2, 3, 4 and so on. So I is changing. Would the value of I affect n? No, n is separate. N is independent of I. That's why we could treat n square as a constant. N is a constant and n square is a constant. So let me repeat that. Please pay attention to that and absolutely get it. 4 is clearly a constant. I'm claiming that n square is also a constant in this context. But I thought n can be variable, man. Yes, it is true. That's why I was careful in saying that in this context. What's the context? The context is where we are taking the sum as I changes from 1 to n. I is the one that is changing. That does not affect n. So that's why n square can be treated as a constant. So 4 over n square is what's called a constant multiple. So that means it's a constant that is multiplying this quantity I square. Okay, so we can pull the 4 over n square outside of the summation because that's a constant. Oh, cool. Can we pull the I square also outside of the summation? Yeah, man. No, man. I square cannot be pulled out because I is changing. So this I square is dependent, is a function of I. So you cannot take that out. So leave I square right in there, but pull the 4 over n square outside. Cool? Now let's go back to the second term. Is there anything that we can yank outside of the summation? 6 a constant, n is a constant, I is not, I is a variable here. So 6 over n can also be pulled outside of the summation. So let's do that. And you have sigma I equals 1 to n of I. And sigma 1, yeah, just leave it as sigma 1. Ain't that interesting? Have we seen anything like this? Sigma I equals 1 to n of I square. Yes, I talked about special sums where we had precisely this kind of a sum. Sigma I equals 1 to n of I square, which was 1 square plus 2 square plus 3 square all the way up to n square. And I told you the formula, n times n plus 1 times 2n plus 1 over 6. So we can just simply plug in that formula for sigma I square. Similarly, did we have a formula for sigma I? Yeah, n times n plus 1 over 2. Did we have a formula for sigma 1? Yep, n. So we'll just plug those values in. 4 over n square times, just as promised, sigma I square is n times n plus 1 times 2n plus 1 over 6. And sigma I is n times n plus 1 over 2. Just plug this in. So now we better get slightly busy and figure out, simplify this. Notice 2 over n must be distributed to all the 3 terms. So when you do, would you agree n and n will cancel? Of course, after we take it inside, multiplies. And so, how about this? I trust you agree with me. The 2 cancelled out with the 6, and so it simplifies to this. Again, n and n go away, and n plus 6 times n plus 1, and 2 over n times n is just 2. So this is what it simplifies to. Can you do this? I know it's a bit, it looks a bit long, and this sigma thing looks complicated and all that. But if you write nicely, have a decent penmanship, put nice equal signs, and write out everything clearly, this is not difficult at all. So here we found the limit of the Raymann sum. We found the Raymann sum. And the next order of business is to find the limit of this, okay, as n approaches infinity. Now, can you tell me what the limit of the first term would be? See how we are relating everything back that we learned? Okay, so here, do we have, if we were to distribute this 4 into each of these terms, do we have a polynomial over polynomial? Same degree, second degree on the top and second degree on the bottom for the first one. And what should be the limit as n approaches infinity of a same degree polynomial, both top and bottom? That's got to be the ratio of the leading coefficients. What does that mean? What's the coefficient of n square on the top after we distribute? 8. What's the coefficient of n square in the bottom? 3. So guess what? The limit of this whole thing as n approaches infinity would be 8/3. Cool. Okay, now let's come here. Do we have a first degree polynomial over first degree polynomial? Okay, same rule applies. The ratio of leading coefficients, coefficient of n after we distribute here, is 6. And coefficient of n is 1. So the limit is 6/1 or 6. Limit of a constant is constant itself. Right? So 8/3 from the first one, 6 from the second, 2 from the third. Ta-da! That's, ladies and gentlemen, is the exact area under the curve. Cool? I hope you appreciate this. Of course, there were quite a few steps. I agree. Welcome to college. Now, let me pick another one. Find the area under the curve, x cubed minus x squared plus 3. I want you to be able to do these kind of problems. That's all in this whole section. If I'll give you a problem very, very, very similar to this. Okay, I'll change the numbers and things like that, but everything else would be exactly the same. Okay, again, we said we'll always use right endpoint sum, delta x times. So the first order of business is to identify what A is. A in this case, you tell me. Yep, you're right, 0. B, 2. Cool. What's the formula for delta x? B minus A over n, which is 2 minus 0 over n, which is 2 over n. Cool. Do we know how to find x sub I? Yep, x sub I is a plus I delta x. A is 0, I delta x, and so that just turns out to be 2I over n. Remember what to do next? We need to find f of x sub I. Cool, if x sub I is 2I over n, can we find f of x sub I? Piece of cake. We know f of x to be x cubed minus x squared plus 3. So f of x sub I would be xi cubed minus xi squared plus 3. But x sub I is 2I over n. We're just going to plug. Cool? So that's going to be 8i cubed over n cubed minus 4i squared over n squared plus 3. So we found f of x sub I. Great. So to find the Riemann sum, delta x, which we found to be 2 over n, times sigma of this guy, right? That's all we do. Okay, once again, like before, can we recognize 8 over n cube is a constant multiple for I cube? We can pull this out. Okay, so 2 over n times, I split this into 3 separate ones, and we can pull this 8 over n cube constant multiple outside, similarly 4 over n square outside, and leave it as 3. Okay, do you recall what the formula for I cube is? Sigma I cube is? That's a square of the formula for sigma I. So n square times n plus 1, the quantity square, over 4. Right? Plug and chug. And then, matter of simplifying. Verify that what I did is right. I distributed and simplified and all that stuff. So came to this. Okay, now I multiplied this out, foiled this out and foiled this out, so that this is our R sub n right now. And the next order of business is to take the limit of this guy and tell me, do we have a second degree polynomial over second degree polynomial? And so ratio would be, the limit would be ratio of the leading coefficients, 4 over 1. Here we have ratio of leading coefficients concept. Notice we need to distribute. So 4 times 2 is 8. So 8 over 3 is the limit for this guy, and plus 6. And turns out to be 22/3. Ladies and gentlemen, will you be able to do problems just like this? In the textbook, just look for something like this and be able to do it, and I'll be a happy man. Maybe in homework I will assign something. All right? Alrighty, that ends this section.